It is the end of 2017, and this has been a great year for Software Engineering Daily. We're taking a break over the holidays, but we're going to be back after New Year's with a lot of new content. And for now, we are replaying a few of the most popular episodes from the 2.5-year back catalog of Software Engineering Daily. And we've removed the ads to make for a smooth listening experience. If you're taking some time over the holidays to listen to some Software Engineering Daily, take a break from your interaction with the family, go for a walk with a nice old episode of Software Engineering Daily, you won't have to skip over any ads or feel obligated to listen to the ads to support Software Engineering Daily. Consider this a vacation for the both of us. We have big plans for 2018. We've got new types of content coming. We've got more in-person events, meetups, but also more of the same. Long-form interviews about technical software topics. That's what I love to do, and I think that's what most people are listening in for. And as we make our way into the new year, I would love to hear from you and know what you're interested in hearing about for 2018, or who you are, or basically anything. Send me an email, jeff@softwareengineeringdaily.com. Join our Slack channel. You can find a link at softwareengineeringdaily.com if you want to talk to more engineers within the community. And you can also sign up for our newsletter, which you can find on softwareengineeringdaily.com at the top of the page. In the newsletter, we will let you know about upcoming live events and other developments within the world of Software Engineering Daily. As always, thanks for listening and happy holidays. Brian Kernighan is a professor of computer science at Princeton University and the author of several books, including The Go Programming Language and The C Programming Language, which is a book more commonly referred to as K&R. Brian, welcome to Software Engineering Daily.
Oh, it's a pleasure to be here, Jeff.
You gave a talk recently called How to Succeed in Language Design Without Really Trying. And in your talk, you surveyed the history of programming languages. As you have witnessed the birth and death of so many programming languages, what are the timeless characteristics that define a successful programming language?
I guess that I would say that timeless means survival. And in fact, one of the things I said in that talk, at least as I remember it, is that most languages don't die. They may go into a sort of moribund or zombie state where there's code written in them that it's too much trouble to rewrite. And so the language, in some sense, remains alive, but barely. Most languages don't seem to die. They just go into that state. But the successful ones, pick your top 10 or 20 or whatever. It's hard to know what ordering there is for those top 10 or 20 languages, but languages like C or Java or Python, those seem to succeed because they're very useful for a wide collection of people. They fit naturally into a bunch of different environments. They're self-sustaining in the sense that there is a community of people that keeps them alive and well. They're all open source. I was just looking earlier at something and thinking, are there any significant languages at all that are proprietary? And at this point, not many come to mind. For example, C# was proprietary for quite some while, but Microsoft has recently made that open source. And I think that's a good move for all concerned.
Have there been any languages whose success has surprised you?
Yeah, I can certainly give you one from my own experience, a language called awk, which Alejo and Peter Weinberger and I worked on. At this point, we started, I think, in 1977. And although it wasn't a throwaway, it was not something that we thought would last. And yet, at this point, it's still very widely used. It's a core Unix tool. I use it myself every day. And that's special pleading, of course, but I suspect lots of people do. And so there's a language which was aimed at a very narrow focus and niche at the time, at least, but that niche seems to have persisted and perhaps even gotten bigger over the years. And so awk survives and even thrives pretty well. A big surprise. No question on that.
In your talk, you also had a slide that showed the volume of languages that we had available in 1961. And these languages were listed on a Tower of Babel-like structure. Of course, in these days, we have even more languages, and we have a taxonomy of languages. And maybe there was some taxonomic structure even back then in this Tower of Babel state. But so today we have, imperative languages, functional languages, domain-specific, typed, untyped. So I'm curious how people categorized languages 50 years ago. Was there some taxonomic structure?
I think that 50 years ago, that would be 1965, I think that there was only a very rough taxonomy. Perhaps you could say there were languages aimed at scientific computing. Fortran would be the obvious one. There were languages aimed at business, COBOL, the dominant example there. Languages that seem to be used primarily for algorithm description, like ALGOL. I actually wrote a real ALGOL program once that ran, but that was sort of it was sort of unusual because ALGOL was more meant as a description, a tool for describing things, but not necessarily executing them. And so I would say that's the taxonomy. Somewhere in there were languages that were, and I don't know how you would describe them in the terms of the time, but languages like Lisp, for example, that are still with us today and didn't fit the standard compile me and run me model. There were just the very beginnings of string processing languages with languages like Snowball in particular, which is a language that it hasn't died. On Hacker News, sometime in the last few months, I saw somebody who had brought it to life and was using it.
You read Hacker News?
I look at it fairly regularly, yeah. It's a way of keeping abreast with what's going on in the field. It's like all such things, kind of a moving target, and it's not clear what you really should be looking at and what you But I do look at it and find it actually quite useful, and gives me a sense of what kinds of things people are interested in.
What do you think people would have been posting on Hacker News in 1965?
Golly.
Is that too random a question?
Well, no, there was no communication in those days.
Well, sure.
And so what would you be doing? You're posting your 95 Theses on the church door or something? That's a great question to which I'm not sure I can give you an answer.
I guess you need a lot of additional contextual information. Like, what context is this Hacker News appearing? Okay, well, anyway, more concretely, what are languages that have persisted since 1965?
Fortran, COBOL, BASIC.
So people say Fortran and COBOL are still around. What are the industries where I can find COBOL and Fortran programmers? Because I would love to have some on the show.
I don't know about COBOL because I haven't written COBOL myself since about 1963 or 4 or 5 or something like that. Fortran is still used in scientific computing. I mean, we're up to Fortran 2013. I can't remember the number of the latest standardization on that. It's used in scientific computing circles. As I understand it, and I'm absolutely not an expert on this, it's still quite a good tool when you want to run really fast on parallel computing equipment used through systems like MPI. I have written a tiny bit of modern Fortran, but entirely for some combination of trivial experiments and pedagogical purposes. I want to see what a program looks like. But the last serious Fortran I wrote was back probably in the 1970s or something like that. But Fortran is very much alive and very much improved. it was a great thing when it was first invented, and it continued to be extremely useful, and as far as I can tell, still is. I have much less experience with COBOL at this point.
Would you describe Lisp as still being around, or do you think it's more of like a conceptual stand-in at this point?
I think it's around if you include things like Common Lisp and Scheme, but I'm not a programmer there. The programs I've written there are even smaller and more trivial and didn't do anything. So, but I think it's still around. And is it widely used in that sense? I don't know. Is it only in the last few years that MIT moved from teaching Scheme in its introductory course to teaching Python? I think that's true, but I could be completely wrong.
Interesting. I mean, the past few years have seen a shift towards functional programming, both on the client and the server in terms of popularity. Do you have any theories on why this is occurring?
I think so. I don't know. I'm absolutely, again, not an expert on functional programming. I have written some unsuccessful programs in Haskell and some slightly more successful ones in Scala, but quite trivial in both cases. I think that the functional programming languages are a place where people experiment with new ways to, new programming, not paradigms so much as new language mechanisms that in some way are meant to make programming safer, more reliable. And the effect of that is that some people do write functional programs for real solid production. I think of some of the financial companies, particularly Jane Street, does that sort of thing. But I would say the majority of the influence of functional programming languages is indirect, that a good idea is explored in functional languages, and because it's a good idea, it finds its way, mutated perhaps, into more mainstream languages. So you could argue long ago that recursion might have had that property, functions as first-class citizens, type inference. There's lots of good things that have come out of the functional programming language experience that haven't really changed the proportion of people doing functional programming, but the people in the mainstream languages are really using those ideas as part of their day-to-day lives.
You mentioned experimentation. What is it about functional languages that lend to a experimentation encouraging environment?
Perhaps because there isn't, as it were, embedded base of experience, and so whatever you're doing is kind of an experiment. That's probably, as I think about it, a little frivolous or facetious, but it's all sort of an experiment because there's nothing in or at least there's not as much in the existing languages that you can map. I mean, if I write a C program, it looks the same as a Go program. It looks the same as a Java program. It looks the same as a JavaScript program. They all very similar. None of them look even remotely like a Haskell program.
Right. Okay, interesting. You described Java as, quote, strongly hyped. And I know that was like half joke, but I think it was also half serious. And I'm like... I mean, you've never written a book on Java, so maybe that's an indirect criticism, perhaps. But why is Java so popular, and why do you categorize it as strongly hyped?
I think the strongly hyped. Well, obviously, it was meant to get a weak laugh somewhere. When Java first arrived in the early 90s, it was thought that it would be a genuinely better way to do certain kinds of computing, that it would be, for example, something that ran in a browser and a way to make programs independent of the underlying operating system. And of course, this scared Microsoft at the time, and Microsoft undertook a lot of things that in various ways subverted Java. Sun Microsystems sued Microsoft. Microsoft eventually settled the thing for a fair chunk of money. And of course, Java never lived up to that promise. We don't run Java in browsers very much at this point. It's still potentially there, but not the norm at all. So I think that's where the hype was, this idea that here's a language which will make it possible for us to do all kinds of interesting computations in a browser. So that part didn't live up to its promise, but Java has become, I think, quite a solid language for certain kinds of server things. Lots and lots of servers are running Java because it is type safe and its efficiency has improved greatly over the years. And so you could actually afford to run it to serve lots and lots of different web serving services, servers. It's all
so
the same.
The JVM, though, the bytecode model, was this a breakthrough or was this something that people were talking about before Java?
I think I shouldn't say lots, but certainly languages had been implemented as various forms of interpreters before that. There are several different ways that you can build an interpreter. For example, awk builds a parse tree and then just walks the parse tree. So that's not terribly efficient, but it's simple. I think Perl did that originally, but I don't actually know for a fact. And that certainly predates Java. There were others, and in fact, we had a version of awk for a while as an experiment that had sort of an internal virtual machine model, not walking a tree, but actually generating something that wasn't bytecodes, but was the same basic idea: make up a machine and then generate instructions and then run them on the made-up machine. So the idea had been around before. And I think bytecodes are simply one of the simplest implementations that you can come up with, pretty easy to work with and pretty efficient.
You said that the single biggest invention within programming on the software side was the creation of high-level languages. How do you define a high-level language, and why is it so important?
So I think the question of how do you define a high-level language? Is my level higher than yours or not? I think that's very much an open question. The comparison I was making there was only between a language like, let's say, C or C++ or Java and an assembly language. And the reason that it is so important is that if you write in a high-level language, whether it's low like C or high like Haskell, you're no longer dependent on the vagaries of the architecture of a single kind of machine. And certainly at the time when this was more important, there were lots and lots and lots of different kinds of machines. The world hadn't stabilized on x86 and ARMs the way it seems to today. So high-level languages moved you away, remove that dependence on the architecture of a particular machine. So you could write your program once, and if you were reasonably careful and the compilers worked, you could then compile it for different machines, and you didn't have to rewrite it. So that was one important aspect. The other important aspect was that it was just easier to write programs at a higher level because you were closer to the way that you, the human being, thought about the problem, further away from the way the machine thought about the problem. And that meant it was just easier to express your thoughts. It also meant that for many people, they could write their own programs. They didn't have to go and hire a programmer. So if I was a physicist or an engineer in 1960 or something like that, and I wanted to have a program that would do some kind of computation, it was counterproductive for me to try and learn the assembly language of whatever the machine was at the time. I would go and hire a programmer. But then along came Fortran, and I didn't have to hire a programmer anymore. I could learn Fortran and express my computation directly. So it's those two things, getting you independent of particular architecture and moving the discourse closer to the way you think about the problem, that those are the contributions of high-level languages.
Yeah, and this probably feeds into the next question too. Computers have gotten more powerful over time, and they've gotten more memory. How has that affected language design?
I think it has meant that we can put things into languages that are better for programmers and sort of worse, in quotes, for machines. That is, we'll use more machine resources, many more machine resources sometimes, to get around or to make something easier for programmers. So the high-level language itself is an example of that. At least when machines were simpler, code generated by a compiler was probably not as efficient as could be generated by a really talented assembly language programmer. But the machines were cheaper, so it didn't matter. And then you can start to add things like libraries of routines. So you can take some general purpose piece of code, string processing, regular expression matching, whatever. One person writes it, does it pretty well. That's good enough for almost everybody. Garbage collection, another fine example of something where we know how to do that pretty darn well at this point. And so you don't have to worry about memory management in most programming languages today the way that you had to in C. And we pay a price for that, but the price is well worth paying because for the large majority of the kinds of things you want to do, the benefit is so high that you just don't have to worry about your memory management or memory allocation at the same level. But that's because the processors are faster, and probably more important, we got just a boatload more memory. You don't have to sort of worry about every bit. Can I afford one more byte? We don't think that way at all.
Are there any ideas or constructs that we're tossing around right now in a theoretical sense where if we only had some order of magnitude more memory or speed, we would be able to turn into some kind of higher level language construct? Or does that get into future prediction and that's too complicated to do? Or
well, it was, I believe, Yogi Berra who said making predictions is hard, especially about the future. It's a cliche, but it's so accurate.
It is.
So I don't know whether a factor of 10 more memory or speed would make a sort of a qualitative difference in the way we do things. I'm guessing not. I think, in fact, sometimes having too much memory can be counterproductive because you tend not to think so hard about what you're doing. You tend to just say, just let me throw something together and see what happens. And so you get bloated software which hasn't really been, where the generalization or the clean part hasn't been found or hasn't shown up yet. And so arguably that kind of stuff in part is supported by just having lots of resources. You don't have to worry about it.
Right. So maybe the future is we have a greater excuse to make messy code.
Well, I hate to be so cynical, but yeah, you could say that.
I don't think that's cynical. So there was also a slide in your talk where you had a categorization of languages over time, from the days of Fortran through C and Java to Go and Swift more recently. And you categorized JavaScript in this separate path from these other languages like Fortran and C and Java. JavaScript was categorized as a scripting language, but more recently, we are seeing JavaScript evolve to do so much more than what anybody would call scripting. As a programming language historian, how do you see JavaScript? Is it an aberration?
That's an interesting question. Certainly JavaScript originally was sort of a scripting language. I mean, the word script shows up in its name, and it really was meant for writing fairly small things. As I understand it, Brendan Eich put it together very quickly, without a lot of introspection, perhaps, but a really good job. And for a long time, it had the reputation of being a language where people wrote really, really awful code because it was possible to throw it together really quickly. The language itself permitted all kinds of stuff. It had academic disrespectability in some sense. And then people started to realize, hey, wait a minute, this language actually has a lot of interesting things in it. You can write really intriguing, useful software and adapt styles from other languages, perhaps callbacks and things like that. Functions are first-class citizens. The JSON notion for how you structure data is very effective, become a universal way of passing data around. And then JavaScript shows up on server machines as well as inside the browser with, I guess, several different things, but the V8 engine from Google, Node.js. And so JavaScript is now kind of everywhere, and people have learned, I think, how to write it a lot better. Again, I'm no JavaScript expert. I've written some modest amount of it. It's pretty easy to do lots of things. Now, at the same time, the language has lots of properties that are perhaps not so desirable. One of I don't know what you call it, a cheap joke or something like that I use in class sometimes is I have two books, one of which is David Flanagan's book on JavaScript, which is about 2.5 inches thick. And then I have Douglas Crockford's book on called JavaScript, The Good Bits, and it's about 1/5 the size. And so maybe that's unfair, but
it's like the width of a magazine.
Yeah, exactly.
Well, it's kind of interesting because it harkens back maybe to the functional thing that you mentioned earlier, where you have this experimental bed, and JavaScript is sort of this. It's kind of object oriented with the prototype model, and then it's also got functional aspects. I mean, when you look at that prototype model versus how object orientation is taught through Java or C++, what does it make you think of? Like, how do you compare those two models of object orientation? I have I think a pretty clear intuitive understanding of object orientation in languages like Java and C++, and I have only a murky understanding of it in JavaScript. So maybe that's the answer. And I think that makes two of us.
Yeah. Okay. Good. I mean, I think the answer is that's partly historical, I guess, and partly I saw object-oriented programming in C++ up close because Bjarne Stroustrup was in the same group I was at Bell Labs, and he used to come in almost every day and explain the implementation of something in his C++ compiler. And I came to understand that, objects are just structures with some help from the compiler, and that's an oversimplification perhaps, but I have a sort of a gut feeling for objects in that sense, which I have never got for the prototype stuff. Very operational, very much coming from a background as a C programmer.
Right. Interesting. Yeah. I do talk to people who have grown up with JavaScript, like, people that are, 20 years old right now or 19 right now.
Yep.
And I get the sense that they have that same intuitive notion for JavaScript's object-oriented model.
I bet. Yeah, I bet.
So that's pretty interesting. So let's talk more about these modern languages that you collected together in this talk. We have Scala, Go, Rust, and Swift. Is there a common thread that you see among these languages other than the fact that they're just modern?
I don't know them well enough to know. Go is the only one that I know moderately well, and even there I can't claim to be a real expert. I have never written programs in Rust or Scala. The biggest Rust or Swift, the biggest Scala program I wrote might have been 25 or 30 lines long, but it looks a lot like Java, so it's kind of cheating. I think the thing that they share a lot, or seem to share a lot, because they're all coming at things from what looks like sort of the same direction. And so there seems to be a lot of mixing or borrowing of ideas from one into the other. They're certainly not the same, but there seems to be some similarity. But I can't go too far down that path or reveal my ignorance even further.
Sure. Well, then let's talk some about Go. I mean, you recently wrote a book about Golang with Alan Donovan. The only other languages you have, well, I shouldn't say the only other. You have also written books about awk and C. Why did you write a book about Golang?
Probably a target of opportunity. I spend most of my summers at Google in New York, and different summers I work on different things. It's in effect like being a kind of an elderly intern. And by good luck, the summer of 2014, I was sitting physically very close to the Go group in New York, and Peter Weinberger's in that group. And of course, Peter and I are old friends and colleagues. And I wound up working for Alan Donovan. He was my mentor for this summer, working on tools for manipulating Go programs, basically doing sort of static analysis kind of things, which is what Alan is particularly interested in. And I had written a tiny bit of Go before, not very much, didn't really grok it particularly well. So spending the summer with Alan was very productive. And we talked about books. And since I had written several books and Alan hadn't, and he was sort of interested in our publisher, my publisher, Greg Dench at Addison Wesley, said, the world needs a good Go book. Now, there are lots of good Go books out there already, but there wasn't one that anybody was super satisfied with. And so Alan and I talked about it a bit, and towards the end of the summer, we started actually roughing out a book, figuring out what would be in it, what would be the general approach, and things like that. And we worked on that fairly steadily for, at that point, it must be close to a year and a half, because the book was finally frozen at the beginning of October of this year, and it appeared at the end of October. So, somewhat over a year, 15 months of work, not uniform speed, and a fair amount over the summer, last summer. That's how it came about, just proximity and an interest in describing a tool that we were both using.
What is special about Go?
I think the things that I think are notable about it in some sense, one, it is a very, in some respects, not 100% by any means, but in some respects, a very direct descendant of C, both syntactically, again, not perfectly, but also in the spirit of how can we find the kind of minimum mechanisms, something that does the job, doesn't have a lot of extra stuff in it. And here I'm sort of echoing the kinds of things I've heard from the creators, in particular Rob Pike, who I know very well, and Ken, who hasn't said very much about it, but I know well. So something that has those good properties of C, but then takes into account or tries to deal with issues that are much more of modern software. One is sheer size. Programs are very, very, very much bigger than they used to be. And so that means that it's hard to maintain intellectual control of big programs. It means that they take a long time to compile. There's all kinds of issues like that. So Go attempts to deal with that in a variety of ways, and it does compile in particular very fast. Now, I don't myself care about compilation speed because my programs are too small, but if I were working at Google or lots of other places, compilation is a big deal. And you know the famous XKCD cartoon about, it's okay, my code is compiling. The other thing that Go does, to my mind, really well is in handling concurrency. Modern computers have lots of processors. My tiny little MacBook Air here has 2, and maybe it has 4, who knows, and obviously there's more and more of those. And so we need languages that make it possible to deal more effectively with the computational resource that's actually there. And so the Go model of coroutines, that is communicating sequential processes in the form that Tony Hoare described back in the 70s, and that Rob Pike had been experimenting with off and on for probably 20 years at Bell Labs. That's something where Go does a really neat job. The model of concurrency, of communicating sequential processes. I have a piece of data, I do something with it, and then I pass it to you over a channel. And now I don't have it anymore, you have it. And that means that a lot of the difficulties of concurrent programming are reduced. They're not eliminated by any means, but for certain kinds of computation, lots of computations, they're easier. It's nicer. So if I'm writing a web server, for example, something that's going to listen to requests that come in randomly, and I've got to be able to deal with your request and somebody else's request and a third request all at the same time. The Go routine mechanism makes that very, very easy. Going the other direction, if I'm writing a crawler that's going out and looking at lots of things, finding files in a distributed file system or pages on the web, the Go routine model, again, works very well for that. It's simpler to write that kind of code with coroutines, Go routines, than it is with threads. Now, this is based on my half-fast experience. I've done this a modest number of times, and it's always been easier to write it with Go routines than it is with threads. And in at least a handful of tiny experiments, it seems to run faster too, but I'm comparing it against Python, and so that's probably not fair. So I think those are the things that, from my standpoint, make Go a nice language. I think it also has properties that make it easier to structure big programs and keep track of where things are and manage interfaces among the components, but I'm not as comfortable talking about that sort of thing. I haven't done enough of it at scale.
Oh.
I can say that if I were going to write a new program, something that I would have used C for 20 or 30 years ago, I would write it in Go without any hesitation whatsoever. That would be great. If I were going to write something that I might otherwise use Python for, at this point is kind of a toss-up. Python is very nice for 100, 200, 500 line scripting programs that have gotten out of hand in some sense. And so I'm comfortable doing that kind of Python, but I think today I might do that in Go instead. It's sort of on the edge.
So if you were to write an operating system these days, you would use Go?
Well, operating system, that's pushing it a bit because I don't know enough about how I would deal with things like the memory management when I have to worry about the garbage collection going on, foot and so on. I'm not sure that fits at the operating system level. But I was thinking if I was going to write a compiler or if I was going to write a text editor or a graphics system or lots of those kinds of things, I'd think pretty seriously about Go.
So what are the major lessons that you learned either about Go or just writing, or programming in particular. When you're writing a book about Go, what did you learn?
It's hard to write books and it's hard to learn a language. I think it takes a long time to get expert enough in a language to be able to have it completely internalized and then play it back in a form that will be useful for another programmer who hasn't yet internalized it. And I don't think I'm at that stage with Go. Fortunately, Alan is spectacularly good, and he really, really understands the language. He understands the applications, particularly the concurrency stuff. And he also writes extremely well. And so the combination, and he's a great programmer, so it made life incredibly pleasant to work with him on that. I think the problem with the book is trying to organize it in the right, find the right structure for it, because programming language is always difficult to find the right linear path through something that's not intrinsically linear. There's always things where you want to talk about something, but you can't talk about it because you haven't talked about something else, and there's cycles in this graph of dependencies. And it's a mess. And I don't think we ever resolved that successfully. The other problem, and I don't think anybody does in any book, so it's not unreasonable. The other problem is that there's a tendency to write a reference manual that's a little friendlier, and I don't think that's what most people need. They can look things up fairly quickly. I think what you want is instead to get a collection of examples that are good. And good means that they illustrate the language, but they illustrate the way the language would be used in real programs. And in fact, the examples themselves are real programs. They're things that a real programmer would want to actually do, might reasonably want to try to write a program like that. And they have to be ordered in a way so that the content fits. You don't have this cycle problem that I mentioned, and that you aren't too far ahead of what the programmer has sort of learned up to that point. And so getting a good collection of examples that are realistic, not artificial, not just syntax, is very, very difficult. And we wrestled with that a lot. I think it helps in this case because we were writing a book where we just assumed that the person reading it knew how to program. If you don't know how to program, this is going to be kind of a uphill slog.
Yeah.
It's just not going to work. So we were not trying to write for people who had never written code. We were writing for people like you know, no problem. It's just another language. And so what you need there is examples where you say, oh, I know how to do that in Java or Python or whatever. Here's how it looks and go. Okay, I see what the structure is of the language. I see the parallels and the differences. And so finding that collection of examples where they're big enough to be interesting, but not so big. I mean, they got to fit on pages. It kept us busy for quite a while. And then, of course, there's all the mechanical stuff that goes into it. How do you can't have programs where the lines are too long because they slop over into the margins. And they've got to break on page boundaries reasonably carefully, and things like that. So we spent a lot of time on just the tools that we used for the actual physical production of the PDF. An awful lot on that.
So I'd like to shift to talking a bit about the Plan 9 operating system. We had a number of listener questions come in about that. And before we get to those questions, can you give an abbreviated version of the Plan 9 story and what your part in that project was?
I can give you the full story of what my part was, which was none.
Okay.
No, I had essentially nothing to do with Plan 9. It was being done by people who were, in the same part of the organization, good friends, physically right around me.
Okay.
But I didn't actually do anything with Plan 9. I think what Plan 9 was, and again, I'm probably oversimplifying to some extent, but Plan 9 was an attempt to take the lessons that had been learned in Unix and generalize them, find those generalizations that made the next version of an operating system cleaner and more elegant and better. And some of those, for example, a good idea in Unix was that devices are files. So we're used to files in the file system, but devices were files as well. So that idea of the file system as a unifying model of accessing computing resource was pushed very hard in Plan 9, and all kinds of things were just files in a file system. Network connections were files in a file system. Shell environment variables, well, the environment was a directory, and the variables, the shell variables were files there. And, the Windows system, the various windows were files in a file system. So they pushed that very hard. And I think that's a neat idea. They tried very hard to get portability right so that you could run the code without any change whatsoever on different kinds of architectures. So there was a 68,000 Motorola-based version, and this was back in the very early 90s, I guess. 68,000 Motorola version, and I'm trying to remember what else. VAX probably, things like that. So the portability aspect's fine. Another thing that they did, and it in fact was invented in Plan 9, was to actually work with Unicode. And UTF-8 was invented by Ken Thompson and Rob Pike and stuck into Plan 9. So I think arguably Plan 9 was the first system to really do a proper job of Unicode. And of course now all systems do that.
Do you think that, what was why didn't Plan 9 supplant Unix? Was this a case of trying to supplant Unix is like trying to replace binary with a ternary?
Yeah. I know what you're saying, and there's an element of that. I think the problem might have been, first, Plan 9 had lots of advantages, but it wasn't like it was an overwhelming advantage. It wasn't like it was going to make your life a factor of 10 easier. And so there's this great deal of inertia to move. Secondly, there was a sort of Procrustean view of things.
What is that word?
Procrustean, the idea that if you're not, this is Greek mythology. You guys should be up on Greek mythology. The idea that this guy Procrustes said to travelers, well, sure, you can spend the night here, but if you're too short for the bed, we'll stretch you, and if you're too long, we'll just chop you off. So the idea is you have to do it his way. And so there was an element of that, I think, in Plan 9 of we have the right way to do it. This is the way to do it, and we're not going to make it easy if you don't want to do that. So, for example, the standard I/O library, which C programmers were used to, was not part of Plan 9. And so if you wanted to import a program to Plan 9, you had to take things written with standard I/O and convert them into BIO, which was in some ways substantially better than standard I/O, but it was different, and it was a nuisance. Similarly, if you wanted to go the other direction, you had to do the reverse computation. Now, eventually work was done, and that was smoothed out. But that barrier between Plan 9 and existing Unix kind of meant that the flow of things back and forth didn't happen the way it could have. And I think a lot of people kind of got tired of making the effort. And I thought, I'm going to write a program, I want lots of people to use it. If I write it on Plan 9, probably lots of people aren't going to use it. And if something is good in the Unix world, it's too much trouble to bring it into the Plan 9 world. So I think that was probably part of the reason that it didn't catch on, in spite of having a really great collection of good ideas and, of course, being rock-solid implementation. So it was just, some barriers and not quite enough benefit.
So we do have some broader listener questions about operating systems. Christopher Reese asked, Some characterize the origins of Unix as a, quote, good enough but very fast Berkeley-based system that competed with the MIT, quote, perfect but very slow Lisp-based system. Is this accurate?
This sounds like a version of the New Jersey versus MIT. I can't remember. So the answer is, I think it's not quite accurate. I think the origin of Unix was simply the desire on the part of primarily Ken Thompson and Dennis Ritchie to make a computing environment which made it very productive to write programs, an environment for programmers. And so they eliminated things that didn't help with that. Part of this was forced because the machines that they were running on were infinitesimal by today's standards. I mean, a big machine that in those days might have had 12K bytes. And so that forced a certain economy and focused your mind on getting rid of things you didn't need. And it also finding those generalizations, the file system, very clean, unified file system in Unix compared to the very complicated file systems that people had before that on sort of commercial operating systems. So I think Unix was mostly an attempt to make something very smooth and easy for programmers and very much a resource-constrained environment. So it was hard to get carried away with anything.
Okay.
So it was not a philosophical issue and certainly not meant to be quick and dirty, just meant to be clean and lean.
Right. So this is somewhat related to the next question, which is by Michael Rosenthal. He asks, do you feel like the Unix one thing well philosophy has been abandoned? And I think he's referring to, well, I don't know, maybe he's referring to computing more broadly, or he's referring to Linux and the things that have evolved off of Unix.
Yeah, it's a good question, too. One of the things that was always said about Unix in the early days that the commands that were provided did one thing well, and they didn't try to do a bunch of different things. And that meant that you could, first, that they were relatively small and simple individually, and secondly, they could be combined in ways that hadn't been thought of by the original creators. And I think to some extent that view of the world has been, well, it hasn't disappeared, but it's often under assault, where you find very big, complicated programs that try to do a lot of different things all within one program, rather than being separable. And that may be inevitable, or it may be just that people aren't, that the mechanisms for combining programs aren't as simple as linear pipelines. Linear pipelines work well for certain kinds of tasks, but they don't handle lots of other things where you actually do have to put stuff together. So I think partly the simplicity of just gluing programs together has been forgotten, but in many ways the world is a lot more complicated too. And so the good old days may have disappeared in part for a reason.
Right. That makes a lot of sense. So let's shift to talking a bit about C, perhaps C++. That, this wouldn't be a Brian Kernighan interview if we didn't talk some about C, since he wrote K&R, which is the famous book about the C language, and it was first published in 1978. Can you take me back to that point in time, and what was your frame of mind like when you started writing that book?
So I think, 78. C had been, as it were, invented or created barely 5 years before that. Because I think the sort of nominal date when the first version of C showed up would be sort of 1973. So it had been around. It was largely inside Bell Labs, although there were Unix systems that had spread outside Bell Labs, and so C was used outside as well. I had written a series of tutorial documents. I wrote one for B, the interpreted language that Ken Thompson had created that is one of the precursors of C. So I wrote a tutorial for that. When C came along, I wrote a tutorial for C so that people could get up to speed more quickly on it. And it seemed that C was getting some use because Unix was getting some use, not huge numbers. And at some point, and I had written at that point 2 books already. I had written The Elements of Programming Style with Bill Plugger, and I had written Software Tools with Bill Plugger. And it seemed like there was enough interest in C that it might be worth writing a book on that. So in probably early 1977 or just before, I arm twisted Dennis and said, why don't we write a book about C? And, this is the smartest thing I ever did. I can tell you, we would not be talking here today if I had not twisted Dennis's arm and he'd agreed. So anyway, we thought about it. The tutorial that I had written for C formed the first chapter of the book. The reference manual, Dennis, just wonderful reference manual. Dennis was a great writer. Formed the back of the book, and then we wrote a lot of stuff in the middle that sort of worked the way through the language, one kind of major feature at a time.
What did you learn from working with Dennis Ritchie? I mean, it's obviously such a brilliant guy. I imagine you learned, not just about C, but about programming philosophy, maybe even broader life philosophy. What kind of things did you learn from him?
Well, certainly learning about the importance of this very clean, spare writing style that he was so good at. That reference manual, which is still in the C book, is an example of that sort of thing. Very clear, very precise. The personal just generosity of the man, that he did all kinds of things in the background for people and never took any credit for it. For example, in the Software Tools book, there's a macro processor that we wrote. I had started a macro processor for the book because I thought it would be an interesting and relevant piece of software, and I couldn't make it work with a damn. It was just awful. And so Dennis went off and in a day or two wrote a macro processor in C, which was very much nicer. And all I had to do was transliterate that into RAT4, and it went into the Software Tools book. And it's still around as the M4 macro processor. That's entirely Dennis's, and he did it as a favor to Bill Plugger and I for the Software Tools book. No credit, no recompense or anything like that, except, that's kind of a fun program for him to write, I guess. So that kind of thing. He had a wonderful, wonderful sense of humor, very dry and hard to relate. If you and your listeners look at the site that Bell Labs put up as memorial for the various talks that people gave as a memorial service about a year after Dennis's death, and that's probably about 2 years ago now, several people spoke of just how spectacularly funny Dennis could be in this very understated way. And a lot of the interesting kind of just subtle asides in papers and code are Dennis's work. That famous comment in the 6th edition that says, "You are not expected to understand this," that's Dennis.
So, but as somebody who gave away so much and also embodied such a humorous spirit, what were his motivations?
I think he just enjoyed the process of doing things, of learning stuff and seeing things happen with it and seeing people use it. I don't think he was ever interested in any kind of credit for it. He got lots, but it was never something that he sought. I think it was just the joy of creating things, of writing code that other people used. He used himself and other people used. And that's my sense of it, that he was just this totally generous guy.
Yeah. So I want to ask you some broad historical questions as our time draws near. Not like existentially, like in terms of the interview.
But you mean the meaning of the universe? 42.
No. Well, so what are the most important things that you have learned about teaching computer science?
Arguably, the things that I've learned about teaching computer science are probably what I've learned about teaching in general. Half the teaching I do is to students who are computer science people, and the other half is people who will never be computer science people. And the same things I think are useful for both, which is to try and explain whatever the topic is, but to try and put yourself in the shoes of the victim and to try to get to know them as people so that you're not talking at a group of faceless bodies, but rather as a group of friends in some sense. And so I try really hard in my classes to get to know who everybody is. So that I can say, hi, Johnny, hi, Susie, or something like that, and really know who they are, talk to them outside of class, keep in touch with them after they graduate. Now, this is, as classes get bigger, this is harder and harder. When I've got 50 or 75 people in a class, I can cope, but when it gets over 200, it's hopeless. But I think that kind of personal touch is a way that actually makes the teaching itself work better, because then it's a communication between two people who are friends in a sense, as opposed to somebody just standing up there and talking. In terms of actual computer science, I think the most effective teaching is the kind that forces the students gently to learn it themselves. So the course I teach most in the spring most years is kind of, it might be called a software engineering course, but the way that the students learn in that course is that they build something. So I tell them that they're going to do group projects. They're going to get together in groups of 3 or 4 or 5 people, and they can build something. It has to be a 3-tier system, but that's everything. And I don't care what languages or tools they use, and I don't care whether it's a web service or a phone app or something else. But they're going to design it and build it and document it and present it in public and let me play with it at the end. And so each person in that class is going to learn something different, but they're all going to learn something. By the end of it, they're going to come out knowing more about whatever it is they did than anyone else in the world.
That is such a good structure. That is the type of project that I learned from by far the most when I was in school. And it actually brings me to the next question I was going to ask. In computer science, what is the difference between theory and practice?
In theory, there is no difference, and in practice, there is. There's some aphorism there.
I know there's some aphorism.
So I think there's probably a false dichotomy between theory and practice. I think the best computer science is the kind that in some way combines those two, where the theory is inspired by some practical problem. You develop a better theoretical understanding of what it is you want to do, and then that feeds back into better practice. A great example from older times is regular expressions. Regular expressions have a theoretical component. You study them, you think about how can I build machines that will recognize things better, and then I'll feed that back in, and I'll make a better regular expression recognizer. And then with the experience of that, then I will perhaps be able to improve my theory again. So regular expression is a nice bite-sized example of a beautiful interplay between theory and practice. That scales up then into the kind of string matching algorithms that you see for DNA sequencing and things like that. That's theory and practice again. Right. Compilation, YAC compiler that Steve Johnson did with a lot of help from Al Aho on the language side. It's another perfect example of theory and practice interacting with each other.
Yeah, so maybe another false dichotomy, but do you see programming as more of an art or a science?
Yes.
Yes, a false dichotomy.
Yeah, it's clearly some of each.
Yeah.
It would be nice if we could make it a science so that we could guarantee that our code would work, run reliably and well, and all of those kinds of things. But to get to that stage, we're not able to do that really. And so that's where the art comes in.
Does computer science belong in the School of Engineering or liberal arts? Does it even matter?
I don't think it matters. It's interesting. I'd say in universities that I know, it tends to be in engineering, although sometimes that's a historical accident. Princeton is weird because although computer science is in the engineering school, it actually has students who are not engineers as well, that is majors who are not engineers, APs as we call them locally, as well as engineers. But lots of schools, it is in the engineering department, but sometimes, and this is probably going back further in time, often where computer science started was whatever department had the first computer. And so it might have been engineering, it might have been mathematics. At West Point, it was geography, just weird things like that. And then eventually these things get normalized because at this point, computer science is a much more mature discipline.
Right. Okay, so I want to close off with one question. It's so some people don't like the question, but other people it's spurred really interesting responses. Do you think that we're living in a simulation?
I guess there's no way to tell. I guess I would say that's not a question that I have anything sensible to say about.
Well, I guess you also answered my follow-up question, which is, if we were living in a simulation, what are some ways that we could test it?
Well, if it's a good simulation, you wouldn't know.
Yeah, I guess that's true.
Yeah, so I'm afraid I can't give you a decent answer on that.
That's fair. Okay, well, then, one last question. And I know these predictions are hard, but what predictions do you have about the future of programming and computer science?
I think the discipline of computer science will be around for quite some while. I think programming will be with us for quite some while as well. I think we will get better at having computers do more of the programming for us so that we get the machine to do our work. We already have lots of programs that do programming for us. That's what compilers do. They're generating assembly language. That's what big frameworks are doing. They're generating a lot of boilerplate for us. I think we'll do more and more of that. Every time we understand an area better, we can mechanize more of the production of code for that so that we can move on to other things that are still unresolved. So I think in that sense, programming will always be around. Will everybody in the world be a programmer? I kind of doubt it, but it may be sort of loosely like the fact that, at least in most societies, almost everybody is able to write, but we have professional writers. And everybody's able to do arithmetic, but we have people who do arithmetic professionally, like CPAs.
Yeah.
And so maybe programming and dealing with computing would be like that too, that there's a level of literacy that everybody's expected to have, but there'll be professionals who do it at a much higher, more sophisticated level. That's my bet.
That's great. Well, Brian Kernighan, thank you for being so generous with your time. It's been a pleasure. It's been a real treat to interview you.
Well, thank you, Jeff. This has really been fun for me, too.